So last few classes we discussed how to solve problems related to bar element, right? So whenever I say a bar element, it means that the force is acting axially. Now we'll proceed with the next element, which is truss element. So what is this difference between bar and truss? So bar is always horizontal or vertical, whereas your truss is an inclined element. Okay, so you can able to see there are bridges which is made by using this truss. Okay, so the force will be acting only in axial direction, but uh, whatever the truss what we consider, that will be in inclined position. Okay, so you can able to see as shown in the figure, right? So mainly it is applicable for some rooftops. So whenever you want to create some rooftop, so we use this truss type of thing, so that you will be attaching the roof on the top of it. Now let us consider this truss element. So which is a one dimension. It is also a one dimensional element. So there are two trusses actually. So it is related with one which is called as a planar truss, the other one we call it as a space trusses. So when I talk about planar, it means that so your truss is inclined with respect to x and y axis. So something like this. So you have only two axes, which is x axis and y axis, and your truss is inclined with respect to that. Okay, so it is like this is a bar actually. This is a bar actually, so which is inclined, okay, to an angle theta. So whenever I consider two axes, x or yz or xz, then we call that as a planar trusses. So if you consider in three dimension, so something related to x, y, and z. So you have three axes, x, y, and z, and your bar element is inclined in such a way that it is inclined with respect to x-axis, y-axis, and z-axis. Okay, so that we call it as a space truss. Okay, so we don't have the space truss in the syllabus, so we have only planar trusses. Okay, so now we will deal with how to solve problems related to planar stresses. So planar is xy direction and your space is xy and z direction. So to solve this related problems, so the first thing is we need stiffness matrix, right? So the first step is to identify what is the stiffness matrix for this truss element. So just derive a stiffness matrix for this. When we consider you have this bar element which is inclined, you know that for this bar element you have two nodal points, nodal point 1 and nodal point 2, right? So in this, so you have two displacements which is u1 and u2. So nodal point 1 will have 1 degrees of freedom which is u1, and nodal point 2 is having 1 degrees of freedom which is u2. So you know that this is inclined to an angle theta. So what is our procedure? Whenever you have an inclined distance, displacement or force, what you will do? You will be resolving it with respect to x-axis and y-axis. So I'm going to do the same. So what I'm going to do? I'm going to resolve this. So resolve this u1 in terms of ux1 and uy1. Similarly, resolving this u2 in terms of ux2 and uy2. So what will be your ux1? So this is your u1 and the angle is theta with respect to that. In that case, your ux1 will be u1 cos theta. And what will be your uy1? So this will be u1 sin theta. Right? Similarly, for this case, this will be u2 cos theta, and this is u2 sin theta. So, and I write it like this. So ux1 will be equal to u1 cos theta, uy1 is equal to u1 sin theta. Similarly, ux2 is u2 cos theta and uy2 is u2 sin theta. So I am resolving it. I am getting two components now, right? So one nodal point one nodal point is having two displacements now, right? So how many is the degrees of freedom? So degrees of freedom here is 2, 2 per node. So one node is having 2 degrees of freedom. So for bar element, we have only one. So since it is inclined, when you resolve it, you are getting 2 now, right? So this is the thing. So there is a difference here, right? Degrees of freedom is 2 per node. Okay, let us write this in a matrix form. So I'm writing it like this: ux1, uy1, ux2, uy2. So this ux1, uy1 indicates your nodal point 1. This is node 1. ux2, uy2 indicates your nodal point 2. You should not write like this. So ux1, ux2, uy1, uy2. It should not be like this. First, you have to complete a particular node, which is ux1, uy1. Next, for the next node. So it should be like this. So this is wrong. Okay. So it should follow like this. Each node should have its degrees of freedom. So continuously. So it should not be separated. Right. So this is my overall thing. So and you have some matrix and you have u1 and u2 as a common term. So what you'll get, this is a 4 cross 1 matrix and this is 2 cross 1 matrix. What matrix size will be here so that I have to get 4 cross 1 matrix. So this is 4 cross 2 matrix. It should have a 4 cross 2 matrix. So writing it accordingly, so we are getting like this. So this is the 4 cross 2 matrix. So I'm writing cos theta 0, sin theta 0, 0, cos theta 0, sin theta u1, u2. So I replace this in terms of a matrix form. So if I want ux1, multiply this cos theta u1, 0, u2. So ux1 is u1 cos theta. That's what we are getting here. uy1 is u1 sin theta. That's what we are getting here. ux2, u2 cos theta, and uy2 is u2 sin theta. We are getting these two terms also. So we are converting this in terms of a matrix form. Now what I'm going to do is I'm going to take an inverse of this. So I want to concentrate only on u1 and u2, right? So actually in matrix, it is not possible for you to take inverse whenever you have a unsymmetrical matrix. Sorry, non-square matrix. So when only if it is when you have a square matrix, you can able to take inverse. But here it is not possible. So what they will do is they will consider this as a transpose. Okay, inverse is considered as a transpose. Okay, so which will be like this. So your u1, u2. So this is transpose of this. So what you'll get? You'll get cos theta sin theta 0, 0, 0, 0, cos theta sin theta. So either you can remember like that, or I can also write like this. I want u1. We consider that. What is my u1? u1 is nothing but ux1 cos theta plus uy1 sin theta. Right? This is resultant. So we resolved it, right? So instead of resolving it, I am writing in terms of a vector form, right? So resultant of this. So ux1 cos theta plus uy1 sin theta. Similarly, u2, what is u2? So ux2 cos theta and uy2 sin theta. This is what I have written in the matrix form. So either you can consider this or you can take a transport and you will get like this. Right? Cos theta sin theta 0, 0, 0, 0, cos theta sin theta ux1, uy1, ux2, uy2. Similarly, let me call this as T. So not to avoid confusion, let me call this as T matrix. So same procedure is also applicable for force matrix. What is your force matrix? Force matrix F1, F2 is T of this same. So similar to this, right? Similar to this. Instead of U, I am writing as F, F. So this is also F, 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 right? That's it. So you'll get the same thing, right? So, but we know that F is equal to K into U. My F is 2 cross 1 matrix, my K should be 2 cross 2 matrix, and your U is 2 cross 1 matrix. This is for bar element. This is for bar element, right? But now it is a truss element. What has happened? It is changed like this. So a F matrix is something like this. T into this, right? So T matrix into Fx1, Fy1, Fx2, Fy2 is equal to K and U 2 cross 1. What is U cross 2 cross 1? So it is T into U, same, right? So my aim is to identify this K matrix, right? So what I can do, I can write it. So I can replace this. I am taking this inverse again. So since it's not a square matrix, so I can consider as a transpose. So T transpose K T. So this is my matrix. Okay. So this is the overall element stiffness matrix for truss. This is for truss element. So I can write as truss element stiffness matrix. Okay. So what we are going to do? So this is the value. So we are writing it. So what is your T transpose? So cos theta I'm writing as C. Okay. C 0 S 0 0 C 0 S into your K matrix, usual bar element K matrix, AE by L 1 minus 1 minus 1 1 into T matrix CS 0 0 0 0 CS. So this is my matrix. Multiplying this, you'll get something like this. So your K matrix, after multiplying all these things inside, you are getting like this. AE by L C square CS CS S square minus C square. So this is the formula. So this is the element stiffness matrix for truss, right? So don't get confused. So lots of things like this. So it is easy to remember, right? What you can do? So just write K is equal to AE by L. So these things are repeating. So what which is repeating? C square CS CS S square. This is repeating. C square CS CS S square. Similarly, C square CS CS S square and C square CS CS S square. Put minus only on these things. So one, this are minus, this are minus. Okay. So this is how you can remember easily this matrix. This is my overall formula, right? So have a note of this. So if I have a truss element which is having nodal point 1 and nodal point 2, it will have two displacements, which is ux1, uy1 and ux2, uy2. So if I know what is the coordinate system for this, which is at 1, it is x1, y1 and 2 is x2, y2. To identify this C is nothing but cos theta. So cos theta is nothing but x2 minus x1 divided by L. Right? What we are identifying? We are just identifying the trigonometric relation. Right? X2 minus x1 indicates what is your horizontal distance. L indicates your hypotenuse. Okay, so length of your element. So this is nothing but adjacent side by hypotenuse. So writing as a formula, that's it. So x2 minus x1 divided by L. Similarly, your sine theta is y2 minus y1 divided by L. So these are two sets of formula. Then what is your L? L is if it is inclined. If you can't able to identify the value, you can use this formula. So to coordinate. So to identify what is your L value. So x2 minus x1 the whole square plus y2 minus y1 the whole square. Right? And the stiffness matrix is K. So K will be equal to AE by L C square CS. So that's what we discussed. And there is another formula for identifying stress. Your stress sigma 1 will be equal to E1 by L1 for element 1 into minus C minus S CS UX1 UY1 UX2 UY2. Right? So have a note of this formula. So we'll be using these formulas to solve problems related to truss. Let's consider this. So you have a true truss element connected here. So they are asking you to identify what is the nodal displacement and the element stresses for this particular truss. They are given what is your Young's modulus. Young's modulus is 70 gigapascal, and the cross section area is also given, which is A is equal to 2 centimeters square. So this is for all the truss element, it is same, right? So they have mentioned the diagram is given, and you can able to see that your diagram is having one force, which is an incline one. So it is similar to whatever we solve in engineering mechanics problems. So whenever you have an inclined force, you resolve it, right? You make it into horizontal and vertical, right? So the same procedure we are going to do. So what I'm going to do is, first step is resolving your inclined forces. Step one, resolve the inclined force into horizontal and vertical component. When you resolve it, right? So you will get, so this side, so when I come, so your angle is decreasing, right? So it will be cos. So 50 cos 30, and this will be sine. So 50 sine 30, right? So resolving it, I'll get the values. So sorry. So you'll get 50 cos 30 and 50 sine 30, right? You will get what is the value with respect to that. So your Px1, so 50 sine 30 is 25 kilonewton, and Py1 is 43.3 kilonewton. So this is my first step. Once I complete this step, so the next one is I have to locate the nodal numbers and the element numbers. So you can able to see the problem. There is no numbering, right? So we have to number it, and you have to number how many elements and how many nodes are there, right? That is my step 2. So let me number this. Let me call this as nodal point 1, nodal point 2, and nodal point 3. So how many elements are here? We have two elements. Element 1, which is connecting nodal point 1 and 2, and element 2, which is connecting nodal point 2 and 3. Right? These are my elements. Okay. So first you identify how many elements are there and how many nodal points, and write it accordingly. Next, identify the coordinate points. So what are the coordinate points for each nodal point, right? So if I consider the first point, so if I consider, let me consider this is 0, 0. This is 0, 0. In that case, this point, right? This point will be 60, 0. 60, 0. Okay. And what about this point? This point is 0, 80. Right? So identify what are the global points. Right? So that is the next step. So when you substitute in mm, right? So I have just directly substituted in centimeter. If you substitute in mm, so we'll add one more 0. So it is 0, 0, 600, 0, 0, 800. So these are my points. So this is my overall value I am indicating here. So for all these things. Next step, you have to write down nodal connectivity table. So this is another important step. So this step is important for addressing your global stiffness matrix. Okay. So nodal connectivity table is, so what is the element and how it is connected. So element 1, I am taking element 1. Element 1, the first node I consider as node 1, and second node I consider as node 2. Okay. In element 2, I consider the first node as node 3 and second node as node 2. So you may say, so what happens if I take it in other way? So instead of 3 here, if I consider 2, and instead of 2 here, if I consider 3, what happens? Nothing will happen. So you will get the same answer, right? But this will be used for addressing your matrix, right? For that purpose, we are writing this nodal connectivity table. Next, I'll identify what is the element stiffness matrix for each element. So this is the step usually we will do for bar element, right? So same procedure. first element stiffness matrix for each element. First element, element 1. So you have two coordinate points. Make sure I consider nodal point 1 as first node. So that is x1, y1. So my x1, y1 is this point, which is 0, 0. What is my x2, y2? Node 2, right, which is 600, 0. So this is my element 1 coordinate system. Now consider it accordingly. Identify what is your L. You can directly find out it is 600, right? But anyway, applying the formula. So L1 is equal to root of x2 minus x1 the whole square plus y2 minus y1 the whole square, which is equal to 600. Okay, that is the total length. Next, what is your C? So C1, because we are concentrating on element 1, C1 is cos theta, which is x2 minus x1 divided by L. So x2 is 600, right? X1 is 0. 600 minus 0 divided by 600. So we'll get 1. So C is 1. What about S? Y2 minus y1 divided by L. So y2 is 0, y1 is 0. So your S is 0. Right? So this is my cos theta and sin theta values. Now, what is my element formula? Let me apply. So your stiffness matrix K12 is equal to AE by L, C square CS minus C square minus CS. So you have this formula, right? Substitute it. So A we know, which is 200, and E converting into Newton per ion square, you'll get 70 into 10 power 3. L is 600 divided by C is 1 and S is 0. So 1 0 minus 1 0 0 0 0 minus 1 0 1 0 0 0. So you'll get something like this, right? So this is my element stiffness matrix for first element, element 1. So okay, so here we consider this 10 power 5 as a common term. So others taking it inside. So which is 0.233. So substituting inside. So we'll get this value accordingly. So next we'll go for element 2. So if I consider element 2, so think about it. First node is 3. So x1, y1 is 0, 800. Second node is 2. So x2, y2 is 600, 0. So be careful in this. So if I consider element x1, y1 is 0, 800 and x2, y2 is 600, 0. So based on that nodal connectivity, we are writing these coordinates points. Now L2, again root of x2 minus x1 the whole square divided by y2 minus y1 the whole square. So identify the same. So we'll get 1000 and your C x2 minus x1 divided by L, you are getting 0.6, and yes, you are getting y2 minus y1 divided by L, which is minus 0.8, right? So these are my values. So now applying the formula, so K32. So why I call this 3? So it is connecting nodal point 3 and nodal point 2. This is my first node, this is my second node. Okay, that's why we indicate 3 2 instead of 2 3. Okay, so just for identification. So this, the formula is same. So AE by L, so C square CS, applying it. So 200 into 17 into 3 divided by 1000. So all these values. Okay, just substituting it. Make sure we identified only C, right? So, but when you are substituting, you have to substitute C square. So which means I have to multiply. So I have to take a square of this. So 0.6 square. This is 0.6 into 0.4. Okay, CS is, sorry, 0.6 into 0.8 minus 0.8. Right, this is the value here. So again, minus C square. So my this is 0.8 square, right? Something like this. So we identify all these values. Sorry, you identify all these values, you will get something, right? So now again, you consider the same 10 power 5 as a common term. Put the other values inside. You'll get something like this. So you'll get a matrix like this. So now we'll proceed. Next step is identifying what is my global stiffness matrix. So what is the formula for global stiffness matrix? It is number of nodes into degrees of freedom per node. Right? For the problem, how many nodes we have? We have 3 nodes. Nodal point 1, nodal point 2, and nodal point 3. Each node has 2 displacements. Right? So it is 3 into 2, which is equal to 6. So the size of my global stiffness matrix is 6 cross 6 matrix. Okay, number of nodes into degrees of freedom per node. So 3 into 2, so which is 6. So global stiffness matrix is 6 cross 6 matrix. Okay, let me consider this. I will assemble in my global stiffness matrix. Okay, so I am just putting this matrix 6 cross 6 matrix. Now you know what is K12. So K12 is this values and K232 is this values. So when you address it, so how to address it? So I will write it like this. This is my element. We start with K nodal point 1, 2, and 3 normally, right? So no need to change everything. So 1, 2, and 3. So 1 is ux1, uy1. 2 is ux2, uy2, and 3 is ux3, uy3. Similarly, here also. So ux1, uy1, ux2, uy2, ux3, uy3. How to address these things? So 1 and 2, right? Similarly, ux1, uy1, and connecting 2, right? So ux2, uy2. Here, it is 3, 2. First 3, right? First is 3, which means ux3, uy3, and this one is 2. So ux2, uy2. So be careful in addressing this. So I'll get same. So this is x3, y3, x2, y2, same in column wise, right? So this is also x1, y1, x2, y2, right? So when you substitute it, okay, that's what I written here, sorry. So when I substitute it, so I'm writing it like this. So this is the terms accordingly. Substitute it. So this comes under here, this part, right? ux1, ui1, ux2, ui2. So okay, no problem. So everything you can fit directly. And 10 power 5 is a common term. Okay. So when you substitute here, be careful. So x3, y3, right? This term. So make sure that blue term alone will be here, assembled here. Right? Next, this you can able to with this violet color, right? So that will be assembled here. So x3 and x2. And this one is also assembled here. And the last one will be assembled here. So which is in red color. Okay. So this is how it will be assembled accordingly. So remaining terms will be 0. Okay. So once you assemble this, you get an overall matrix like this, right? So this is my overall K matrix. So you will get, after adding it, you will get something like this. Okay. So see the complications. So you are dealing with 6 cross 6 matrix. Okay. So okay, this is your K. That is enough. Next, I'm going to determine my global force matrix. So what is my force matrix? So you have 3 points, x1, y1, sorry, x1, y1, x2, y2, and x3, y3, right? So which is indicated nodal point 1, nodal point 2, and nodal point 3. So when you look at the problem, so you have force only at nodal point 2. So remaining it is 0, right? Remaining it is 0. So just substitute it accordingly. So only for that, so just I'm substituting it. Okay. So when you substitute, make sure now you consider the right hand side as positive, upward as positive. Remaining, you have to put negative sign. It's not like a previous bar problem. You will get answer directly. Here, the direction is very important. So downward direction is a negative term. So I will put minus 43.33 into 10 power 3. So this is my term. 0, 0, 25 into 10 power 3 and minus 43.3 into 10 power 3, 0, 0. So this is my term. Okay. So it is applicable only for nodal point 2. So others are 0. So this is my force matrix. Now what I can do, I can just substitute, equate F is equal to K into U. So let me substitute it. So this is my F matrix, right? This is my F matrix, 0, 0, 25 into 10 power 3 minus 43 into 10 power 3, 0, 0 is equal to, this is my K matrix and this is my U matrix. So F is equal to K into U. We identify. Now let us apply our boundary conditions. What is my boundary condition? Nodal point 1 is fixed. When it is fixed, what it means? Your x1 is 0 and y1 is also 0. So since it is fixed, ux1 and uy1 both are 0. In that case, what I can do, I can eliminate the first row, first column, second row, second column. So this gets cancelled. Similarly, go to nodal point 3. Nodal point 3. So what nodal point 3 says? It is also fixed. ux3 is 0 and uy3 is 0. Which means your fifth row, you can strike it out. Fifth column, strike it out. Then last row, last column, strike it out. Whatever the remaining term, that alone has to be considered for your answer. So what are the remaining term? Let me write it out. So 25 into 10 power 3 minus 43.3 into 10 power 3 is equal to, so your remaining k terms into this. So now what I can do, I can equate it. So I can just write it as in an equation, separate equation. So multiplying it, 10 power 5, 0.283 ux2 minus 0.067 uy2, right? So I'm writing like this. So this is my first equation. And similarly, you can consider the second equation. This is my equation 2. All these two equations, you will get what is the values of ux and uy, right? That gives you the displacement for this truss element. We will go for element stresses. So for element stress, so you know the formula. So element is equal to E1 by L1 minus C minus S CS ux1 uy1 ux2 uy2. This is for element 1. So just substitute it. So your Young's modulus is 17 to the power 3. Your length is 600. You already identified what is your C and what is your S for element 1. Substitute that. So minus 1, 0, 1, 0. And now you know what is the values for this ux2 and uy2. That you substitute. The others are 0, 0, 0, whatever the values we got. When you substitute, you will get what is your stress. So stress in element 1. So multiply it. So minus 1 into 0, 0, 0 into 0, this 0. So 1 into minus 0.325. So you'll get only this 0.325. So this becomes 0. So then multiply, you will get what is your stress in element 1. Similarly, for stress in element 2, it is E2, L2, same. So make sure when you write here, so stress in element 2, your first node is 3, second node is 2. Okay, so you should write that formula accordingly. So this is ux3, uy3 and ux2, uy2. Okay, so you make sure whatever you consider first, that will be coming first. So otherwise the entire problem goes wrong. So just substitute it accordingly. So you know what is the value. So you already identify what is where C and S. Substitute all these things. Now multiplying it, you will get what is the answer for element 2. So this completes the problem.